Hello, AP Psychology students. I have a serious question for you. As you look at the images of these two people, which one is happier? Like, just kind of go by your gut instinct. Which one do you think looks happier? Now, in my mind, it's very clear to me that one is probably clinically depressed. I mean, he just looks really sad. The other one to me looks kind of whimsical. Well, if you're like most people, usually 95% of my class chooses the left one as being happier. So why does this happen? Well, as it turns out, just like everything in our body, that the left visual field goes to the right side of the brain. And the right side of the brain is better at reading facial expressions. So not only are we paying more attention to this left face, but we're also paying more attention to the left side of his face, in both faces. In this one, he has a smile. In this one, he has a frown. So in the left visual field of both faces, we're going to see either a smile or a frown, and therefore most of us are going to choose the left one as being happier. It's quite obvious to me. So today we're going to look at the divided brain. This is a really interesting study that has shown us some of the differences between the right and the left hemisphere of the brain. The corpus callosum is the last brain structure that we have not discussed yet. It is a bundle of fibers, and it is in your diagram that looks like this, and it looks like this from the side view, or what's called the medial view. If we were to look down from the top of the brain, we would see that there are several fibers, neuron fibers, going from the right to the left side of the brain, and this is something called the coronal brain. It's if you cut the brain in half from the front to the back. So this is really important for just very quickly sending information from the right to the left hemispheres of the brain and back. We normally don't have to think of anything about it really, unless we have a procedure called a cerebral commissurotomy. So for people with severe epilepsy, they might have this procedure done, and it surgically severs the corpus callosum. So basically what is done is the surgeon will put a hole in the skull and then take a scalpel and clip these neuron fibers. Now, that sounds really barbaric and primitive, but it is actually sometimes the best option for someone that has severe epilepsy. So I'm actually going to put online a video of a man who has had a cerebral commissurotomy done and some special testing that is done, but I am not going to embed this into your PowerPoint right now, but it's a Scientific American Frontiers video, and it features a doctor called Dr. Gazzaniga, who is from Dartmouth and has been at the forefront of split brain research. So going back to the PowerPoint, what did Michael Gazzaniga watch? I really, really highly recommend that you watch that video. So when someone has the corpus callosum cut, as we see in this picture, we have the right visual field going to the left hemisphere, and so we'll see if you watch the video, you'll see that the individual stares at a dot in front of them, and any image from the right side will go to the left hemisphere. Any image from the left side will go to the right hemisphere. And then what happens? If it goes to the left hemisphere, in this case, the apple, then the person can name the object. They can say, that is an apple. But if they have it go to the right hemisphere, they can't name it, or can they describe it? If it goes to the left visual field, the right visual field and the left brain, they can name and describe the object, and they could point to a picture of it. But the main thing is, if it goes to the right brain still knows what it is. It can't name it, it can't describe it, but it could point to a picture of it. So that is the mystery of the division of our right and left side of the brain. So what we have here is something called cerebral lateralization. There is a test in your packet called the Wagner Preference Inventory. This would be a good time for you to take out that test and to see if you have a preference for activities that involve the right brain or the left brain. It's very easy to do, and you just follow the instructions for scoring it. And I recommend that you do that. And I also recommend that you take a look on the next page to see if you would agree that you have preferences for those left or right side brain activities. So when we look at the preferences on the left side of the brain, we see things like logic, mathematics, language. Definitely, you do need to know that Broca's and Wernicke's area are on the left side of the brain, and the right side of the body and visual field. On the right side of the brain, we have preference for spatial activities, nonverbal activities, facial expression and understanding facial expressions, music and art appreciation, and of course, control of the left side of the body or visual field. So we call this lateralization because these types of activities seem to lateralize or become sort of cemented on either the right or the left side of the brain. Now, where we can especially see problems with these sides of the brain is, for example, if someone has a stroke. If they have a stroke in the frontal lobe near the Broca's area, they're going to have a hard time being able to communicate using language. If someone has a stroke in, say, the parietal lobe of the right side of the brain, they might have problems with visual spatial mapping. And so, like I've said before, oftentimes we know what a part of the brain does when we look at people that have a tumor or a stroke in a particular part of the brain, and then we can see what is affected. So here is a sort of description of if you have a preference, you're more likely, if you have a left visual preference like I do, I like words. I like to do things in order. I like to take small bits of information and put them into a logical order. And I do work easily with symbols. I like working with mathematics. I like working with music. Those are both symbols. The thing that people who have a right brain preference, what they have told me is that they really lose sense of time. They also like to do hands-on activity, and they're really good at looking at the big picture. And this is definitely my husband. I think it was his real strength in his job was to be able to see the whole picture of these various computer systems and how they all fit together. So either way, whether you have a left brain preference, right brain preference, or no preference at all, there is still important things that you can do and contribute into any kind of team or occupation that you work in. I'd like to talk about the specialized functions of the speech and language areas. So again, these are mostly lateralized in the left side of the brain, and I'm going to talk about each of them separately: Wernicke's, the angular gyrus, and the Broca's area. Okay, so let's take a look at what it takes to read a word out loud. So number one here is that we have the visual stimulation that comes back to the occipital lobe where we first see the word. This is the visual cortex. And as any of us read a word out loud, the visual stimulation, it comes back to the occipital lobe first. Then we are wanting to make this into auditory code, and the angular gyrus works alongside the Wernicke's area to help us do this. Now, the Wernicke's area is very important for interpreting auditory code. If someone were to have a stroke in this region of the brain, when a person talks to them, it won't make sense to them. If they try to read something, it won't make sense to them. So this is a very difficult part of the brain to have damaged. The Broca's area controls the speech. So we're reading the word out loud. We understand it because of the Wernicke's area in the temporal lobe, by the way. And then the Broca's area, which is in the frontal lobe, helps us to actually control the speech and the muscles for speech, including your mouth and your tongue, via the motor cortex. And Broca's area has the unique ability to produce speech and language, whether it is written or oral. And so if someone has a stroke in the Broca's area, it is an extremely frustrating experience because they can understand language and they know what they want to communicate, but they cannot communicate it because of the damage to the Broca's area. So what we call this is aphasia. I've actually witnessed two people actually, who have had a stroke or a tumor in the area that pushes up against the Broca's area. One of them was a roommate of mine from college. She was quite young. She was only in her early 30s, and she had just had a baby. And in the process of the recovery from giving birth, she had a blood clot that actually traveled up to her brain and got stuck in the Broca's area. It was so frustrating to visit her because she knew what she wanted to say, and she just cried when she couldn't say it. So she basically just waved us away and said, with her actions, go away, I can't talk to you. Now, thankfully, she was able to recover her speech ability because she was young, and when you're young, you are able to recover from a stroke fairly well. I've seen someone else with Broca's aphasia, and his was caused by a tumor that was pressing up against the Broca's area. In his case, he just couldn't simply find the words that he wanted to say, but when his tumor was removed, the pressure on that area was relieved, and he was able to then again complete his thoughts. Wernicke's aphasia is again, a type of aphasia where you're not able to fully understand language. So by default, you're not going to be able to speak language very well either. Both of these are really, really difficult situations to deal with because language is so central to our existence as humans. And finally, I'd like to finish with brain plasticity. This girl, her name is Bindi, and she actually had half of her brain removed in something called a hemispherectomy. Now, the only part of your brain that you would have removed, of course, is your right side. The left side is too dangerous to move because it has the speech functions in it. So sometimes for very, very severe epilepsy, and she was having something like 50 seizures per hour, you might have your right brain removed. This surgery does still occur. It occurs here in the Twin Cities. So what happens after something that radical, or even something like a stroke or tumor removal, is that we now know that the brain can adapt and reorganize itself. First of all, experience can sculpt features of the brain. Let's say you are a stringed instrument player and you play the violin extraordinarily and you practice 4 hours a day. Well, it's possible that the right side of your brain that corresponds with your sensory cortex and your motor cortex, because you're pressing on the strings with your left hand for most people, that part of the brain is actually going to have stronger connections and more neurons devoted to it. Here's another really fascinating finding, and this is definitely one that is newer within the last 10 years or so. Healthy neurons can reorganize and compensate for damaged or missing ones. In the case of this woman here, she actually had the right hemisphere removed when she was quite young, about 5 years old. She learned to walk again. She did not learn to use her left hand again, but she did learn to walk again. And the part of her brain that helped her use her left leg is now in this part of the, I'm sorry, to use her left, her right leg rather, is this part of the brain here that is on the left side, and it helped her to use her right leg again. Neurogenesis, the birth of new neurons, we now know can occur into adulthood. So if indeed we are learning new skills or new information, we might indeed grow new neurons either through that learning of the new skill or new knowledge, or because of damage. We do know that plasticity declines with age. If you know someone who had a stroke as an elderly person, it's far less likely that they're going to recover from their stroke. If you do know someone who has a stroke at a younger age, and I've known several, probably at least a half dozen, they are going to have a much better chance of recovery than someone who is older. So I will put Brandy's story online, and this is basically the end of our unit on the brain, but I will have one more screencast on the structure of the nervous system. Thank you for your attention.